going to start off this section by talking about eigenvectors and eigenvalues. If you have a matrix A, or square matrix A, sometimes you can multiply it by a special vector, which is called an eigenvector, and it will be the same as taking that vector and just multiplying it by a scalar. That's a scalar and is called an eigenvalue. Okay, so I'm not into computers, but if you have this big big matrix, and it has, it's 100 by 100, and you want to multiply it by x1, x2, up to x100 to get the answer, well, there will be 10,000 calculations to be computed. It'd be 100, well, it'll be over 100 times 100, because you'd have to multiply this number by x1 and this number by x2, and eventually those numbers. That's 100 multiplications. And then you'd have to do 100 again, and eventually the last one, 100 multiplications. This is 10,000 multiplications. And when you dot this with x1 and that with x2, all the way that with x100, you have to add them up. That's 99 additions. And you have to do it 100 times. One for the first row, one for the second row. So 100 times 99 is 9,900 additions. Or you could take lambda, figure out what lambda is, to get the same answer that we got on the left. This only involves one multiplication, second multiplication, 100 multiplications, no additions. 10,000 versus 100. 100 multiplications and 0 additions. Alright. Now, as far as I'm concerned, one studies eigenvectors and eigenvalues for the beauty of it. Okay, so how I see it, everything in this section is just theoretical. Doesn't matter if somebody can apply it or not. Now, if we have this equation, lambda times x, and I bring this over to the other side, you have ax minus lambda x. Now, we know that if we have matrix A times matrix C minus matrix B times matrix C, C is on the right side in both of these products, we can factor out C on the right side. And we get matrix A minus matrix B times C. Now, I can't do that over here because that's not a matrix. In other words, if you have 3, 4, 7, 2, that's A, and you want to take away lambda, you want to take away 4, what does this mean? And the answer is it's gibberish. It has no meaning whatsoever. Okay. And I do have one little typo. If I bring this to the other side, then the right side is 0. But not on the bottom line, because this is gibberish. Okay, so how do we get it not to be gibberish? How should I be thinking about that? Okay. Now, we know that x is the same as I times x. Okay? This matrix and this matrix are the same. When you multiply two matrices, you get a matrix. I can multiply on the left on both sides of the equation by lambda. Okay, lambda x is the same as lambda times ix. So, instead of saying ax equals lambda x, in terms of solving such an equation, we're going to say lambda times ix. Now I can bring this to the other side, and I get ax minus lambda ix equals the 0 vector. And now I can factor out the x on the right-hand side. On both of these equations, x is on the right. I can factor it out. So that's the equation that we always want to solve. Okay. Now, something about an eigenvector. You don't want to get boring, dry eigenvectors. Now, we know that A times the 0 vector is the 0 vector. And if you multiply lambda by the 0 vector, you get the 0 vector. A times the 0 vector is the 0 vector. And any scalar times the 0 vector is the 0 vector. But we don't want x in the line above, in the equation at the very top, to be the 0 vector. It's just a rule. And we don't want x to be the 0 vector. So, when it comes to this equation, so this equation gives us this equation. We want to solve this equation. You'll be given A. That's all you'll be given. We want to solve this equation. But we don't want only, now we know x equals 0 is an answer, but we want other answers. X equals 0 is the trivial solution. We want other answers. Well, a homogeneous system of equations has non-trivial solutions if and only if the determinant of the matrix is 0. To get non-trivial solutions, we want this to equal 0. Okay. Now, remember that if you have a matrix, whether the matrix is A minus lambda I or not, let's suppose the determinant of this matrix is 17. Or let's call it negative 17. If I multiply the first row by negative 1, then the sign changes. If I multiply the second row as well by negative 1, the sign changes back to negative. If I multiply the third row by negative 1, it becomes positive. That is, the sign keeps changing. Now, if I multiply all the rows by negative 1, well then I'll get negative A minus lambda I, which is lambda I minus A. Okay? Alright. Now, since I want the determinant to be equal to one another, equal to 0, it doesn't matter if I change the signs. If the determinant of this matrix is 0, not 17, it's 0. If I multiply the first row by negative, I get negative 0, which is still 0. If I then multiply the second row by a negative, it changes to positive. Multiply the third row, it becomes negative. The last row becomes positive. The bottom line is it doesn't change values. It is best for determining, let me not say determining, it is best for calculating their determinant to, instead of computing the determinant of a minus lambda I, we'd rather we do lambda I minus a. Okay, so defined. And this, when you solve this, it'll be a polynomial in terms of lambda, and you set it equal to 0. So you can find the lambdas that way. That is, you can find the eigenvalues. You can find the eigenvalues that way. Okay, enough of talking. Let's look at a number of numerical examples. So we'll start off with an easy one. Suppose A is a 2 by 2 matrix and it has all ones. That is A. So to find the eigenvalue, you want to set 0 to equal to the determinant of lambda I minus A. Well, here is minus A. Now, basically, lambda I has just i's on the diagonal, zeros elsewhere, and then you take away A, which is all ones. And you get lambda minus 1, 0 minus 1, 0 minus 1, and then lambda minus 1. If for a moment you ignore the lambdas, you have negative 1, negative 1, negative 1, negative 1, which is exactly negative 8. Now put the lambdas on the diagonal. So this is what we get. And the determinant, like always, of a 2 by 2 is this product, lambda minus 1 squared minus the product of those two negative 1's, which is positive 1. And this is supposed to equal 0. Well, if this minus that is 0, immediately say that these two things are equal to one another. Now, next question is, what can you square to get 1? The answer is plus or minus 1. Well, that tells me that what I'm squaring, lambda minus 1, can equal plus or minus 1. That is, lambda minus 1 is 1, or lambda minus 1 is negative 1. And you should know, these aren't big numbers. They don't exceed 2. 2 minus 1 is 1, so lambda is 2. 0 minus 1 will give you minus 1. So lambda is 1. Lambda is 2, or lambda is 1. Let me put this on the top. Lambda is 2, lambda is 1. Now that we found the lambdas, we want to find their corresponding vectors. When lambda is 2, you'll get a vector, an eigenvector. Sometimes you might even get a sum of eigenvectors. So now we're going to proceed with lambda equaling 2. When it comes to the determinant, it's best to use or to find the determinant of that matrix. When it comes to finding the eigenvector, we want to solve, imagine the I over here, bring this to the other side, and factor out the x. Ax equals lambda ix. Ax minus lambda ix equals 0. I factor out the x. So I want to solve this homogeneous system of equations. That is, I want to solve this. Well, A is 1, 1, 1, 1. That's A. And I want to take away lambda I. That is, I want to take away lambdas from the diagonal. Now, what I will say is lambda is 2. That is, I want to take away 2 from all the diagonals. Which happens to give me negative 1, 1, 1, negative 1. And let me solve that up here. Sorry. Augmented with 0. Okay. So we have negative 1, 1, 1, negative 1, all zeros. I want to get that entry to be 0. Well, just add the top to it. That is, add row 1 and row 2. Row 1 was not changed. Row 2 becomes a row of zeros. And the next step is I would multiply row 1 by negative 1. So I get 1, negative 1, 0, 0. Augmented with 0. Okay. Row 1 has a leading 1. Row 2 does not. So when I look at column 1, I see a leading 1. When I look at column 2, I do not. We'll say that big X is x1, x2. So what we know is x2 is a free variable. Call it R. And the first line says 1x1 minus 1x2 is equal to 0. That means x1 equals x2. x1 equals x2, which is R. Now, let R equal some friendly number other than 0. If R is 1, then we get 1, 1. That is an eigenvalue associated with lambda equals 2. In fact, any multiple of that vector works. Because remember, this answer says that x1, x2, big X's are R. I can factor out the R and I get 1, 1. That is, X, the eigenvector, can be any multiple of 1, 1. Okay, so I'll do one more step. We are done with finding the eigenvector associated with lambda equals 2. The one more step that I will do is check it. I want you to see that this really works. And also, on homeworks and exams or whatever, you should check it. That way you know if you're right or not. I've always been amused when students or classmates of mine tell me they have no idea what they got on the test. And then when the test comes back, they get a 96. Like, how don't you know it? Didn't you check any of them? Okay. So I'm going to compute A times X. This was A, and X is 1, 1, and I get 2, 2. And now I'm going to compute lambda times X. Lambda is 2, and X is 1, 1. When I multiply each of those entries by 2, look, always put that division on. I get 2, 2. And look, they're equal. It really worked. Instead of multiplying the A by the special vector 1, 1, I just multiplied 2 by the vector 1, 1, and I got the same answers. Pretty neat. Okay, so it checked. Now we're going to assume lambda is 1, and find the eigenvector for that. The eigenvector associated with lambda equals 1. Okay, so we want to solve a minus lambda I augmented with the 0 vector. And now lambda is 1. That is, we want to solve a minus 1i, or just I, augmented with 0. Well, here is a, and I have to take away 1s from the diagonal. Okay, minus 1, minus 1. This is the system I need to solve. 0, 1, 1, 0. Okay, of course something went wrong here. We had lambda minus 1 squared is equal to 1. See if I erase that or not. Yeah. So lambda minus 1 is either positive 1 or it is, oh, I said lambda was 0, didn't I? Or lambda minus 1 is negative 1. This is either 1 or negative 1. Well, 2 minus 1 is 1, so this lambda is 2. And 0 minus 1 is negative 1. So I'm sure I said that, but somehow I wrote 1 down. For obvious reasons, I said 1 so many times, but nonetheless wrong. Okay, so we want to take away, this one's all wrong, we want to take away 0 i's. That is, we want to take away 0 from the diagonals, which doesn't do anything. We just get 1, 1, 1, 1, augmented with 0, 0. Okay, sorry about the typo. Now, let me say something very clear. I've always maintained, and it says it on the top left, that the eigenvalue, that is the value for x, cannot be the 0 vector. Never ever said that lambda can't be 0. Lambda can certainly be 0. Now, if I just do row 2 minus row 1, since the rows are identical to one another, when I subtract, I get the 0 row, and this matrix is in RREF form. First row has a leading 1, second row does not. Look up the first column, yeah, there's a leading 1. Look up the second column, no leading 1. That means that that second column, x2, because we have x1 and x sub 2, the x sub 2 is a free variable. Call it R. The first row says x1 plus x2 is equal to 0. Bring over the x1, bring over the x2, and you get that x1 is negative x2. But x negative, but x2 is R. So big X, when R is equal to 1, is negative 1, 1. In fact, since x is negative R, I can factor out the R and say I'm a multiple of that. Okay, a multiple, any multiple of 1, negative 1. So here, I could have let x be 2. I could have let x be, R be 2, and I would get negative 2, 2. Negative 1, negative 1. So for each eigenvalue you get, that is, for each lambda that you get, you have to then find the corresponding eigenvector. Sorry. For each lambda you find, which is called an eigenvalue, you have to find the vector, the eigenvector that corresponds to that eigenvalue, which is a lambda. You get lambda, next step is to find the eigenvalue. Okay. Suppose A is equal to 0, 1, 2, 0, 0, 3, and a row of zeros. You want to define the eigenvalues. First, you let 0 equal to the determinant of lambda I minus A. Well, here is negative A, negative 0, negative 1, negative 2, negative 0 is 0. Here I'll write negative 0. You'll see why. Negative 3, I'll even write it there. Negative 0, negative 0, negative 0. And on the diagonals, you put lambda. It turns out that this negative 0 is just positive 0. This negative 0 is just positive 0. This is 0. But that's lambda minus 0. Okay, now, this in front of us is a special matrix. Everything below the diagonal is 0. That is, I can easily write down what this determinant equals. It's the product of what's on the diagonals. Just the product of those three values. And lambda minus 0 is lambda. So I'm multiplying lambda by lambda by lambda. And I get lambda cubed. That there, what this determinant gives you is called the characteristic polynomial. You should clean this up as much as you can. In other words, if you got lambda minus 7 squared plus 4 times lambda minus 4, you should multiply it out and get something like lambda squared plus 11 lambda minus 14. I'm probably wrong, but that would be what you would call a polynomial, characteristic polynomial. Don't use this one. Clean it up first. Okay, now, what we have at the very bottom left is that lambda is equal to the number 0. For the record, we've done 2 problems and both of them had lambda equals 0. It's called a coincidence. Lambda is equal to 0. Okay, so now we want to find the eigenvector. We want to solve A minus 0I augmented with the 0 vector. But 0 times any matrix, including their identity matrix, is the 0 matrix. A minus the 0 matrix is just A. That is, we just have this. We just have this. That matrix is A minus 0I. I augment it with 0. And the first thing I would do is I'll divide row 2 by 3. I get 0, 1, 2, 0, 0, 0, 1, 0, 0, 0, 0, 0. And then for row 1, I can kill this off by taking away 2 row 2's. I'm going to do row 1 minus 2 row 2's. And work it out, make sure I'm correct, or you know, that you can do it on your own. I get this. This matrix is in reduced row echelon form. The first row has a leading 1, the second row has a leading 1, the third row does not. We'll call the variables x, y, and z. Column x has no leading 1. That's the free variable. Column y has a leading 1. There it is. Column z has a leading 1. There it is. That x is equal to r. The first line tells me that y is equal to 0. The second line tells me that 1z, or z, equals 0. Z is equal to 0. So big X is R0, 0. And if I let R be 1, I get 1, 0, 0. And that's my answer. When lambda is 0, X is 1, 0, 0. Okay. This is hard for a lot of students, so the best thing for me to do is to do lots of examples, which means one more. Suppose A is equal to 2, 2, 3, 1, 2, 1, and 2, negative 2, 1. And we want to, we want to find the determinant of lambda I minus A. We want to set it equal to 0. Okay. In my opinion, the easiest way to do that is to negate A. Change the sign of each entry or multiply each entry by negative 1. And then put lambda on the diagonals. Since this is a 3 by 3, we write down the determinant once again. We repeat the first two columns. We repeat that. Lambda minus 2 and negative 2, negative 1, and lambda minus 2, and negative 2, and positive 2. We multiply those three, and we get lambda minus 2 times lambda minus 2, which is lambda minus 2 squared, times lambda take away 1. And when we multiply those, we end up with negative 4. And when we multiply those three, we end up with plus 6. And from there, we take away this product, which is 6 times lambda minus 2, minus 2 times lambda minus 2, plus 2 times lambda minus 1. So let's do this multiplication on the bottom. Lambda minus 2 squared, that gives you lambda squared minus 4 lambda plus 4. And if I take that result and I multiply it by lambda minus 1, so first I'll multiply everything in here by lambda. what I'll get is lambda cubed minus 4 lambda squared plus 4 lambda. And now I take away 1 times this. That is, I multiply everything here by negative 1. So I'll get negative lambda squared plus 4 lambda minus 4. And if I add those up, I will put the result here. I get lambda cubed minus 4 minus 1 is minus 5. Lambda squared, 4 plus 4 is 8, so plus 8 lambda minus 4. Okay, let me not forget to add on the 2. That's the first bracket. This mess up to the minus 4 was just the product of those 2 factors. Now I took away 4 and added 6. That is, I added 2. Okay, let me get rid of my side work. Let's do some more side work. But first, just a very, very quick comment. I would not call, let me do it another color. I would not call this the characteristic polynomial. Clean it up first, which is what I'm doing. Clean it up first. Then you call it the characteristic polynomial. Okay. I have 6 of these, and I'm taking away 2 of the same thing. So I have 4 of them. 4 times lambda minus 2. And as it says at the end, I'm adding on 2 times lambda minus 1. So I have 4 lambda minus 8 plus 2 lambda minus 2. So I'm left with 6 lambda minus 10. 4 plus 2 is 6. You take away 8, you take away 2 more, you took away 10. 6 lambda minus 10. Okay, the problem is that's not what I got before. Oh, excuse me, maybe it is. So 0 is equal to lambda cubed minus 5 lambda squared. If you have 8 lambda and you're taking away 6 lambdas, you have 2 lambdas. This number is negative 2. Let me put it down here. And you want to take away negative 10. This happens to be plus 8. Plus 8. That is the characteristic polynomial. If this was my problem, the first thing I would consider, since there are 4 terms, is to try to factor by 0. I take that back. Try to factor by grouping. And that's not going to work. That will not work. You can try it, but it wouldn't work. Then you should use the rational root theorem. And then when you do find the root, you use synthetic division. Pre-calculus. This is just pre-calculus. Okay, so it turns out that this fact is the x plus. So first you find out that lambda, actually, I won't even say this is a characteristic polynomial. I won't even say that, I'm sorry. If you were to use pre-calc techniques, you would find that lambda is 1, lambda is 2, and lambda is 4. Okay, if lambda is negative 1, then lambda minus a negative 1 must be a factor, which is lambda plus 1. And that's what I wrote. And if lambda equals 2 is a root, then lambda minus 2 is 0, is a factor, I mean to say. And if lambda equals 4 is a root, then lambda minus 4 is a factor. This here is the characteristic polynomial. It's the value of the determinant that's in factored form. This is it. And here, unfortunately, we have 3 different eigenvalues. Lambda is equal to negative 1, lambda is equal to 2, and lambda is equal to 4. So now, one by one, we are going to find the corresponding eigenvectors. First, you find the eigenvalues. Then, for each eigenvalue, you go back and you find their eigenvectors. Okay. So, in a moment, once the eraser clears, we'll start on that. Okay, let's clean this up first. So lambda is equal to negative 1. So we want to solve a minus lambda I augmented with the 0 vector. So if lambda is negative 1, we get a plus 1i, because taking away a negative 1i is the same as adding 1i. So I write down a 2, 2, 3, 1, 2, 1, 2, negative 2, 1, and I add 1 to each entry on the diagonal. And this gets augmented with the 0 matrix, the 0 vector. And doing the arithmetic, actually I'll say equals here, adding the 1s to the diagonal gives me this. And I augment this with the 0 matrix. Now, if you were to reduce this matrix, you will get the following. This video, I reduced a lot of matrices. I can't keep reducing them. If you reduce this matrix, eventually you will get this augmented matrix. Row 1 has a leading entry, row 2 has a leading entry, row 3 does not. Column 1 has a leading entry for some row, column 2 has a leading entry for some row, column 3 does not. So Z is equal to R. The first row says 1x plus 1z is 0. Bring their z over, you get x is negative z. But z is R. X is negative z. And the second row just says 1y is equal to 0. Okay, y is equal to 0. So x, big X, when r is 1, is negative 1, 0, 1. And that's the answer to the first problem. When lambda is negative 1, the eigenvalue is negative 1, 0, 1. That is one eigenvalue. If instead I let r equal negative 1, then I would get 1, 0, negative 1. I could have let r equal 10. So x can be negative 10, y would still be 0, and if r is 10, z is 10. That would be another solution. All I'm saying is you and your classmate can both do the problem 100% correctly, yet you get different eigenvalues. If your classmate's eigenvalue is a multiple of yours, that's okay. They can be a multiple of one another. You don't have to all get the same eigenvalues. Sorry, eigenvectors. The eigenvectors have to be a multiple of one another. Okay. Now, lambda is 2. Let us find the corresponding eigenvector when lambda is the number 2. Okay. I'm ready to put my answer down. We want to solve a minus lambda I augmented with 0. So I write down a and I take away 2 from the diagonals and augment it with zeros. This gives me 0, 2, 3, 1, 0, 1, 2, negative 2, negative 1. 1 minus 2 is negative 1, augmented with 0. If we were to reduce this, what we will get is 1, 0, 1, 0, 0, 1, 3 over 2, 0, and a row of zeros. A column. Row 1 has a leading 1, row 2 has a leading 1, row 3 does not. So column 1 has a leading 1 in it for some row, column 2 does, column 3 does not. Call the variables x, y, and z. So this means that z is r. The second row, okay, let's start with the first row. 1x plus 1z, which is x plus z, equals 0. So x is equal to negative z, but z is r. The second row says that 1y plus 3 over 2z is 0. Bring this to the other side, y is negative 3 over 2z. Except z is r. So this would tell me that x is equal to, or x can equal to. Now we don't want fractions. I'm looking at y, negative 3 over 2. What can you multiply the negative 3 over 2 so you'll have no fractions? Remember, whatever is in the bracket is r. I mean, after all, it's negative 3 over 2 times r. The answer is 2. If r is 2, the middle term will be negative 3. If r is 2, the last term will be 2, and x will be negative 2. Negative 2, 3, 2. If you used 1, you'd get negative 1, negative 3 over 2, and 1. I didn't like fractions, so I let R equal 2. Now we do this all over again for lambda equals 4. Lot of work, absolutely. So since lambda is 4, we'll take is a minus 4 times I. This should be 4. Which means on the diagonal, I'm not taking away 2 anymore. I'm taking away lambda, which is 4. The reason I claim this is cleaner than doing 4i minus a is we don't even have to figure out what minus a is. We just wrote down a. What's in there, minus some silly error on my part, is a. This is supposed to be a. And I am supposed to take away 4i. That is, I take away 4 from each diagonal entry. I get negative 2, 2, 3, 1, negative 2, 1, 2, negative 2, negative 3, which is augmented with the 0 vector. Now, I reduced this a little bit, and I got this result. Let me go a little bit further. The third row is not going to change. And to get the second row, I'm going to divide by negative 2. I'm going to divide by negative 2. And in the first row, I'm going to add the first and the second row, because that will make that a 0. And what I get is negative 2, 0, 8, 0. And then if I divide by negative 2, I get that. 1, 0, negative 4, 0. So let me erase my arithmetic, my side work. Row 1 has a leading 1. Row 2 has a leading 1. Row 3 does not have a leading 1. Column 1 has a leading 1 for some row, namely row 1. Column 2 had a leading 1. Column 3 did not. That means that Z is equal to R. Let's do the second row. The second row says 1y minus 5 over 2z is equal to 0. That means y equals to 5 halves z. If you subtract two quantities and you get 0, they must be equal to one another. So y is 5 over 2 times z, but z is r. The first row tells me that 1x minus 4z is 0. Again, you subtract two quantities, and you learn that difference is 0. They have no difference. Oh, you mean they're equal to one another? X is equal to 4z. But z is r. I'm going to erase side work. Now I can write down a particular solution. I haven't used that word up to now, but I should have. One particular value for x where r is 2. That way the 2's will get canceled out. 4 times 2 is x. 5 over 2 times 2 is just 5. And R is 2. So there it is. 8, 5, 2. Had 3 eigenvalues. I found their corresponding eigenvectors. Okay, let's do some more. Gonna talk about two matrices being similar to one another. Okay. Matrix B is said to be similar to matrix A if there exists a non-singular matrix P such that if you take, it's similar to matrix A. If you take matrix A and on the right you multiply by P and on the left by P inverse, hence P had to be non-singular, you get back B. You get back B. Okay, if you can take matrix A and multiply on the right by P and on the left by the inverse of P, matrix B and matrix A are similar. If A is equal to 1, 1, negative 2, 4, and you're given that P is 1, 1, 1, 2, and you're asked to find a matrix similar to A. Well, first you have to find P inverse. It's 1 over the determinant. 1 times 2 is 2. 1 times 1 is 1. 2 minus 1 is 1. 1 over 1, don't worry about. Switch the positions on the main diagonal. Instead of 1, 2, it's 2, 1. And on these entries, leave the numbers where they are, but change their signs. And you don't even have to multiply by the 1. It won't do anything. Okay, so now matrix B, if I define B to be P inverse AP, which is 2, negative 1, negative 1, 1, and I multiply by A, which is this, and I multiply by P, which is 1, 1, 1, 2. Whatever I get, and I work this out, I get 2, 0, 0, 3. That is B is equal to this. B is similar to A. Why? Because I took A, I multiplied on the right by P, and on the left by P inverse, and by definition, whatever I get, it's said to be similar to A. It's a definition of similar. Okay. Well, if B is similar to A, is A similar to B? If B is similar to A, does that guarantee us that A is also similar to B? And that question motivates the next theorem. Okay, theorem makes 3 statements. Theorem 1. A is similar to A, if B, I'm just going to write S circle to mean similar. If B is similar to A, then yes, A is similar to B, and statement C says if A is similar to B and B in turn is similar to C, then A and C are similar. The transitive law. Now, the proof of 1. Okay, you really have to see this one. I'll write it out in the greatest details. Let P equal I. Well, the inverse of I is I, because what do you remember? The inverse of I is such, if that's the inverse of I, it's because when I multiply it by I, it gives me back the identity matrix. I times I equals I. So if this is A, well then that's A inverse. That is, the inverse of the identity matrix is the identity matrix. Now, A times P inverse times P. So whatever I get here, whatever this equals, it's similar to A. Whatever this equals is similar to A. Well, P inverse is I times A times I. Well, I times A is A times I. That's A. So, whatever this equals, namely A, is similar to what's in the middle. Or I should say A is similar to what I get. A is similar to A. Okay. Now we're saying if A is similar to B, okay, if B is similar to A, then A is similar to B. So here's the proof for part B. Part 2. Proof for 2. B similar to A implies that B is equal to P inverse AP for some matrices A and P. Okay, so let's look at this some more closely. We know that's true. Well, I'm going to solve for A. I want to get A. On the left, I'm going to multiply by P on both sides of the equation. And on the right, I'm going to multiply by P inverse. So I have P, B, P inverse. Now I have the associative law. I can group those two together. I can keep A in the middle, and then I can group those two together. But this is I, and that's still A, and this is I. Well, that's A. Okay. So, A is equal to P, B, P inverse. But isn't P inverse inverse, and B is B, and B is B, and that is just P inverse. Now, P inverse is just a matrix. Okay, this implies that A is similar to B. Why? Because P inverse is just a matrix. Call P inverse C. this says C inverse times B times C is equal to A. Therefore, A is similar to B. Don't get caught up. But this can't be an inverse. I mean, it isn't. P inverse is a matrix. You have the inverse of some matrix times B times that same matrix on the left. That is P inverse. And it equals A. A is similar to B. Okay, proof number C. The proof of 3, not C, excuse me. Let's see what that's going to look like. The proof of 3. A is similar to B. This implies A is equal to P inverse BP. And B is similar to C implies that B is equal to some Q inverse times C times Q. Okay, so I have B in the middle here, but I can write that instead. So A, I'm just rewriting this, but instead of B, I'm going to put that. A is equal to P inverse times any way of writing Q, B. I just wrote B differently, times P. Okay, now this is P inverse Q inverse times C times QP. Now, whatever is over here, I want the inverse of that to be there. And then you go, oh, yeah. When you have A times B inverse, you switch the B into A, and you inverse them. So I switch the Q inverse and the P inverse. Oh, excuse me. What I have right here is in this form. So I can switch the A and the B. I can switch them and not have inverses anymore, but then put the inverse on the outside. I can switch the P and the Q, the P inverse and the Q inverse, ignore their inverses, and put the inverse out here. Again, what this equals is switch the P and the Q and inverse both of them. But that's exactly what I have there. CQP. Now, QP is some matrix. Oh, and over here I'm taking the inverse of that matrix with C in the middle. So since A equals that, that implies that A is similar to matrix C. Neat theorem. Okay, let me give another definition. Matrix A is said to be diagonalizable. if it is similar to a diagonal matrix. Just because you take matrix A and you multiply on the right by some are non-singular matrix and you multiply on the left by the inverse, the matrix you get back doesn't have to be a diagonal matrix. I mean, after all, if I take matrix A, 3, 1, 2, 4, and I multiply by the identity matrix on the right, and I multiply by the inverse of the identity matrix on the left to get that. That's too hard. We know that A is similar to A. And if A is not a diagonal matrix, well, A is similar to one then. So to remake that statement, since A is similar to A, and A doesn't have to be a diagonal matrix, like 3, 4, 1, 2, which is not a diagonal matrix, is similar to 3, 4, 1, 2. Okay, but now A is similar to many matrices. It doesn't have to be similar to let me think for a moment, to a diagonal matrix. Okay, a clear case would be if A is 0, 0, 0, 0. No matter what P is and no matter what P inverse is, you're gonna get the zero matrix, which is never diagonal. It is a diagonal matrix. It has the same entries there. So there's a case where no matter what P and P inverse are, there are matrices that you cannot multiply them by P and P inverse and get a diagonal matrix. Now, I want to say one last thing, because what I said was a little bit sloppy. Just because the matrix, you have some matrix A, say that's A, and you take A and you multiply it by some P and by some P inverse, and you get 7, 1, 4, 2. That does not say A is not diagonalizable. Why? Because maybe if I pick different P's and P inverses, it would work. It is possible that if I take 3, 4, 1, 2, and I multiply it by Q inverse and Q, then I get 3, 0, 0, 13, or 8, 0, 0, 13. Now I can say, yep, A is diagonalizable. So just because you can find some P and P inverses, that does not show that A is diagonalizable. That doesn't mean it isn't. Try different matrices. Okay. Now, here is an amazing theorem, which I'm not going to prove. At least I don't think I am. It's just simply an amazing theorem. Nothing like it ever before. Theorem. And n by n matrix A is diagonalizable if and only if the matrix A, if it has n linearly independent eigenvectors. Okay, so if A has, you calculate their eigenvectors of A, and if they're all linearly independent, then A is diagonalizable. But that's nothing. In this case, the case where A is diagonalizable, that is, A has n linearly independent eigenvalues. In this case, A is similar to the diagonal matrix D whose entries on the diagonal are the eigenvalues. Eigenvalues of A, of course. Okay. So far what you have is that P inverse AP is equal to D. So what's P? Where P is the matrix whose columns are the eigenvectors. We're going to look at and add some examples of this. And we're going to do that by looking at, say, earlier examples. We had A equal to 1, 1, 1, 1. And that implied that the lambdas were, I think, 1 and 0. 0 and 2. Lambda was 0 and lambda was 2. Now, let's see if I can find the eigenvectors. 1, 1 for 2 and negative 1, 1. Okay. So I had negative 1, 1 and 1, 1. Okay. So now I'm going to let P be, I'm going to let the eigenvectors be the columns of P. That's the first eigenvector, and here is the next eigenvector. That is P. The determinant of P, because I want to find P inverse, is this product, which is negative 1, minus this product, which is 1, it's negative 2. So P inverse is going to be 1 over negative 2, which is negative a half. And then I switch the 1 into negative 1. And these 1s and 1s, I switch their sign. Now, if I compute P inverse times A times P, in the end, I'm going to get the eigenvalues on the diagonal, 0 and 2, and zeros elsewhere. And that is simply unbelievable. I get negative a half, 1, negative 1, negative 1, negative 1. That's P. I multiply this by A, 1, 1, 1, 1. And I multiply this by P, which is negative 1, 1, 1, 1. I can bring the negative a half in front of everything. When I multiply those two matrices, I get 0, 0, negative 2, negative 2, and then I multiply by negative 1, 1, 1, 1. Just because it'll make numbers smaller, I'll actually scale now. I'll multiply this matrix by negative a half. And I get 0, 0, 1, 1. And then I multiply by this matrix. Negative 1, 1, 1, 1. And I get 0, 0, 0, 2. Which is my matrix B. It has the eigenvectors on the diagonal. Now let me be clear about something. When it came to matrix P, I put down, this was P, I put this eigenvector down first. And that corresponded with 0. Oh look, the first diagonal entry was 0. Then I put down 1, 1. I put down this eigenvector. And it corresponded with the number 2. Look at that. There's my 2. The eigenvectors end up on the diagonal. Okay, the eigenvectors end up on the diagonal. And that is just something beautiful. Okay, so now the question is, I'm going to give you a matrix A. I'm going to ask, is this matrix diagonalizable? And either it is or it isn't. A is equal to a row of zeros, 0, 1, 0, 1, 0, 1. Okay. Is this matrix diagonalizable? Well, let's find the lambdas. So first we want to do lambda I minus A. We want to set this equal to 0. So here is the negative A. Oops. Actually, negative, negative. You really have to put the negative there on the diagonal, even if it's 0. That way, you can sneak in the lambdas. Now, this matrix is lower triangular, because everything above the diagonal is 0. So this determinant will be the product of these three entries. Lambda minus 0 is lambda times lambda minus 1 2 times. 2 times. Okay. So, and it equals 0. So that implies either lambda is 0 which happens when lambda is 0, or lambda minus 1 squared is 0. The only number you can square and get 0 is 0. So lambda minus 1 should be 0, and that happens when lambda is 1. Okay. Now, note that the multiplicity of lambda equals 1 is 2. Lambda minus 1 came up 2 times, and 1 time. Now, we need to get 3 linearly independent eigenvectors. We need to get 3 linearly independent eigenvectors. Now, if lambda is equal to 2, what we're trying to solve is a minus lambda I augmented with 0. That is, we take away 2 from all the diagonal entries. 0 minus 2, and then 0 and 0, 0, and 1 take away 2 is negative 1, and 0, and then 0, 0, minus 1, because 1 take away 2 is minus 2. And yes, I do have one typo. There's a 1 here. Okay. So we have this matrix. We have this matrix, and it's augmented with 0, and we want to solve this. I'll divide row 1 by negative 2. That will give me this. I'll divide row 2, by negative 1, or I'll multiply it by negative 1. It will give me this one. And I will take 2 times row 3, which will put a 2 here, and I'll add row 1 to it, all of row 1. So when I add those, here, I'll do it right here. Here is 2 times row 3. Here is row 1. And when I add them, I get 0, 0, negative 4, 0. And then I will divide by negative 4. So I get 0, 0, 1, 0. Okay, now the biggest problem was, and you're all screaming, why are you plugging in 2 for lambda? I accidentally saw that too. Lambda is 1. Let us work with lambda equals 1. I'm very sorry about that. Lambda is the number 1. That means I just take away 1 from the diagonals. Matrix A stays the same almost, except on the diagonals. So all my diagonal numbers are going to be wrong. I take away 1, I get negative 1, 0, 0. Okay. Now something went very wrong here. So I get that matrix A except the diagonals. I take away the number 1. Get negative 1, 0, 0, a row of zeros, 1, 0, 0. Okay, now what I'm going to do is I'm going to multiply row 1 by negative 1, and I get that matrix. Second row I put on the bottom, and then for the second row I just add these. And I get, I guess I didn't need to do that, I get another row of zeros. Okay, so this is what I get. Row 1 has a leading 1, nothing else does. So x, y, and z. Y and z are free variables. Let v equal s, and y equal r. And the first row says that x is 0. Okay. So we need to write down that answer a little bit differently. The variables are r and s. I have to write big X as a multiple of r plus a multiple of s. And the first value better be 0. So I'll do 0 r's plus 0 s's. The second entry should be just r. 1 r plus no s's. And the third entry should be s, which is 0 times r plus 1 times s. So basically, I get back two eigenvalues. When lambda is equal to 1, I get back 0, 1, 0, and 0, 0, 1. Get back two eigenvalues. Okay. Now, I want to talk about why I did that one first. Because since A is a 3 by 3, I need to come up with 3 linearly independent eigenvalues, eigenvectors. And when lambda is 1, since the multiplicity was 2, I might run into troubles there. I might run into trouble. Okay? So what I did was I checked that first. Now lambda is equal to 0. That is, I take away 0 from the diagonal. So a minus 0i augmented with 0, that's just a augmented with 0. Now, this matrix is in reduced form. Almost. I mean, you can interchange those two rows if you prefer. Keep row 2 the same. And now it is done. Row 1 has a leading 1, row 2 does. Column 1 has a leading 1 for some row, and column 2 has a leading 1 for some row. Column 3 does not. Call the variables x1 and z. So this tells me that z is equal to r. The middle row says 1y equals 0, or y equals 0. The first row tells me x, 1x, plus 1z is 0, so x is negative z, but z is r. So x is negative z. This tells me that x is, if r is 1, this tells me that x is negative 1, 0, 1. Now, a few moments ago, I had that x was equal to r times 0, 1, 0 plus s times 0, 0, 1. Well, if s is 0, if s is 0, and r is 1, that gives me, this cancels out, and 1 times 0, 1, 0 is that. And if s is 1 and r is 0, the r cancels out, and I just get 0, 0, 1. Get two of them. Let r and s both be 3, and then let r be 4 and s be 2. Just get two of them. And they're clearly independent. Okay, now, when lambda is equal to 0, we get negative 1, 0, 1. This is clearly independent because this vector here is the only one that affects the first entry. It's the only one that has a non-zero entry. So, yeah, I found 3 linearly independent eigenvectors. Okay, so since we found 3 linearly independent eigenvectors, we conclude that A is diagonalizable. Pretty neat stuff. It's really beautiful stuff. It is simply amazing. Now, let us look at another problem. Suppose A is equal to 1326. Is A diagonalizable? So first we compute lambda, I lambda minus A, the determinant for that. Well, here is minus A, and we put the lambdas in front. Only on the diagonals, excuse me. Only on the diagonals. And this determinant is lambda minus 1 times lambda minus 6 minus negative 2 times negative 3, which is positive 6. And what we get here is lambda squared. Add those two numbers, negative 7 lambda. Multiply the two numbers, you get 6. Take away 6, that cancels, and you want it to equal 0. So you can factor out a lambda from each of these, and you're left with lambda minus 7. So either lambda is 0 or lambda is 7. Okay, well, if lambda is equal to 0, we have A minus 0I augmented with the 0 vector. The 0I is the 0 matrix. A minus the 0 matrix is A. We get 1, 3, 2, 6 augmented with 0. I will do row 2 minus twice row 1. Well, when you double the first row, you get the second row. So when you subtract, you'll get a row of zeros. 1, 3, 0, and my row is zeros. This is in reduced row echelon form. Y can be any real number. X plus 3y is 0. Bring over the 3y, you get x is negative 3y, for y is r. Letting r be 1, we get that. You can let r be 11 if you prefer, or negative 1, or 2/3. But let it be 1, it's friendlier. So, we found the first eigenvalue. Now we're going to let lambda equal the number 7. Going to let lambda equal 7. So I'm not taking away 0i, I'm taking away 7i. That means I'm taking away 7 from the diagonals. I'm taking away the number 7. Minus 7, minus 7. I get negative 6, 3, 2, negative 1. And I augment this with 0. Okay, if I divide row 1 by negative 3, I'll get 2, negative 1, 0, 2, negative 1. Oh, the two rows are the same. So if I just subtract, the bottom row will be zeros, and the top row is that. If I divide the top row by 2 to get my 1 now, I get this. Okay, let me go to the very top, please. Y is equal to R. The first row says 1x minus the half for y is 0. That implies x is half of y, but y is R. So if I let R equal 2, half of 2 is 1, and R is 2. I get that the second eigenvalue is 1, 2. Now, the question is, are these two eigenvalues linearly independent? Are they linearly independent? And if they are, then my answer is yes, A is diagonalizable. So, are these two vectors linearly independent? So, I write them down as a column. I augment it with 0. And so basically what I'm solving is C1 times the first vector plus C2 times the second vector. And I want to know whether or not I get 0, 0. I mean, when I do get 0, 0, do I get it because C1 and C2 are 0? Well, if I add the two rows, I'll get a 0 right there. So the first row did not change. When I add, I get 0, 3, 0. If I divide the second row by 3, I get that. And now, if I do the bottom row minus the top, row 2 minus row 1, I did that because 0 minus a negative 1 is 1, and 1 minus 1 is 0. If I did it the other way, row 1 minus row 2, I would have a negative 1 here. Okay, 1. Oh, you mean 1C1 is 0, and the second line says C2 is 0? So the answer is yes, A is diagonalizable. This completes the section on eigenvalues, eigenvectors, and diagonalization. Enjoy.